Hello, I am Shayan Tapadar, and for our digital image processing term project, me and Aryaman, we were working on a universal noise removal algorithm with an impulse detector. Firstly, I would go through the paper a little, that's our report, and then I'll go to the code. So, the originally existing work is something on a bilateral filter for noise removal. And the paper that we worked on was a trilateral filter, which is a development on the bilateral filter by adding one more weight. So let's just go first that we introduced a statistic called ROAD, rank ordered absolute differences, which is basically a difference, a summation of differences between the intensity values of pixels in a neighborhood. We use a 5 cross 5 neighborhood in our code, and then based on that we kind of order them in ascending order and then take the minimum four weights and add them up. That gives us the road value of the pixel. Next we have the weights. We have a spatiometric term and a radiometric term as defined here. These are directly taken from the bilateral filter. And additionally we introduce a term, the wi, the omega I, which is the impulsive weight term, which is based on the road statistic. Also, we introduce another value called the joint impulsivity, because we cannot directly multiply the weights, because the bilateral filter, when we change it to the trilateral filter, if we directly multiply the weights, the radiometric term would suppress the non-impulse pixels too. So we need to have a joint impulsivity value which can actually reduce the effect of that weight. So we have the jxy, and finally the weight that we get is this. Okay, the rest of it I'll go forward as I explain the code. The code is uploaded here. It's the GitHub profile, and let's go up. I'll go through each of the code files directly on GitHub. So let's start with the UNF filter. So this code basically implements the UNF filter. You take in the image, the neighborhood. Here the neighborhood is 2, which basically means 5 cross 5 neighborhood, 2 into 2 plus 1. It also takes an input as SS, SI, SJ, which is the sigma S, sigma I, and the sigma J values. Sigma R is directly estimated here using this particular formula. Sigma R is 2 into the standard deviation of noise. So what we use out here is the idea that sigma R kind of can be estimated as twice the standard deviation of the quasi-Gaussian noise of the image. The sigma GN value is given out here. This is the standard deviation of the quasi-Gaussian noise. uh, we calculate that in this particular file, estimate noise standard depth. Let's go there. Yeah, so this basically estimates the standard deviation of the Quasi-Gaussian noise, just an implementation of the formula given in the report. And we pass that back to UNF filter, and we calculate the sigma R based on that, which is basically twice of that. The SS, SI, and SJ values are given out here. We have used directly these values. For SS, we have taken zero point 0.7. For SR, as I just explained, we have taken 2 into the standard deviation of Quasi-Gaussian noise, and SJ we have taken as 50. These are directly taken from the paper we are implementing. For SI, I'll go through forward. After taking this, we pad the image with zeros and then pass it here. Here the slice basically is taking the 5 cross 5 neighborhood of the pixel and then passing it to the get UNF kernel function. So let's go to the get UNF kernel function. Yeah, the get UNF kernel function here basically estimates the values of the spatiometric weight, the radiometric weight, and the impulse weight. You can see WS, WR, and WI. The road value is calculated, the J value is calculated, all based on the formulas as given in the report. Here, the point to be noted is the creation of SR. So, as you can see, we are passing SI, let's say, not SR, sorry, SI. So, here you can see that for SI, I am using this particular formula. So, let me just go over it. For Si, the values that were found experimentally to be the best were between 25 to 55. So what was done is basically we calculated the road value of the pixel, and I used 60 as a threshold to determine whether the pixel is an impulse or whether it's an uncorrupted pixel. As you can see from this graph, all of these are basically impulse pixels and these are uncorrupted pixels. So you can see that 60 is quite a reasonable value to consider as a threshold, and thus I use 60 to consider that any value above that is an impulse and any value below that is an uncorrupted pixel. And then all I did is subtract 60 from the road value of the pixel and pass it through a sigmoid function and basically just clamp it between 25 and 55. So this is a sigmoid function, and then I scaled it to 30 and then I shifted it by 25 to get the sigma I value. You can see this implementation out here. Then we calculate the j, and finally we take the weight, as you see, just the multiplication of them, and we return each. This part is a kind of summation because we need to normalize this weight. So this is basically a normalization of the weight. We add them all up and then finally divide by the summation. We divide each of the multiplied weights by the total of the weights in the neighborhood, and then we pass it back to the UNF filter. The UNF filter then just applies it over that neighborhood and returns us the image. Let's go to main then. Let's go over this part. Let's go. So first we have P. P is the probability of impulse noise, which basically determines that the value of P is point. Let's just go by value. So 0.04 here indicates that every pixel has a 4% probability of being an impulse. Then we have this particular variable called stdev equals to 10, which is basically the standard deviation of the Gaussian noise which is added to the image. These two values will be subject to change, as we can change these two values to see results for various noises in the image. The neighborhood is set to 2, SS is taken 0.7, 25, and 50, as you can see, as I had just said in the report. The image used is the lena.tif, which is pretty much a standard image. Uh, and this is just some error, I don't know why. Anyway, just gotta go back. Just bear with me. I don't know why this error occurred or whatever. This is probably some network issue. So it's back. Let's go to main again. Yeah. So that was image origin. Next, we have this particular function called impulse noise. Impulse noise just adds random impulse noise of probability p to the image. As you can see, we take two variables, k and q, and then if k is less than p, that is, if the random value generated is less than the probability, then we consider that that particular pixel will just get changed. That's just additive impulse noise. The next would be addition of Gaussian noise, which is again taking in standard dev, stdev as the input, and then we add zero mean and standard deviation value equals to stdev Gaussian noise to the image. This is just that. And we come back. Next, we apply UNF filter on the image. So we are comparing the UNF filter with the median filter. The UNF filter, as described in the report, was applied twice. Once with SS equals to zero point 0.7 for impulse noise, and once with sigma S equals to 4 for the Gaussian noise. So as it was found that sigma S values in the range 0.5 to 1 works well for impulse noise, and higher values of 3 to 5 are better for Gaussian noise. So we apply UNF filter twice on the image, once with sigma S and once with sigma S equals to 4, to finally get our target image through the UNF filter. And this median filtered variable stores the same image, but this time going through a median filter. We are using a 3 cross 3 median filter. The my median filter code has the median filter, which is again a simple median filter which takes in neighborhood size as input and runs a 2 into neighborhood size plus 1 into the. So here we are passing 1, so a 3 cross 3 median filter. This is basically just the code of the median filter, and what we return is the median filtered image. Let's go to main.m. So now we have the UNF filtered image and the median filtered image. We calculate the PSNR values and compare. Here, we are also the only other function that's left is myconf2d. So let's just explain that. This is a custom 2D convolution function. We are not using the conf2 function of MATLAB. Instead, we defined a myconf2d. This basically just is the same as conf2 same. Conf2 with the option as same. So we pad zeros to the image and then just convolve the image with the kernel. This works the same way as conf2 image kernel and same, but still just because we were not using any standard official functions, we were making custom functions for everything like impulse noise and this. So we made a myconf2d too. So that's it with our main. Now let's just go to the implementation. I have the code opened already. So we'll try with 4% probability of impulse noise and 10 standard deviation of Gaussian noise first. And then we'll go through some other values of noise too, just to see the results. The code will take some time, so yeah, sort of wait. So yeah, we have got a result. You can see quite an improvement out here. We are getting almost increase of 1.3 PSNR decibels. It's pretty evident from the image also. You can see this is pretty very quite noisy, and this is not that. This is quite clear. So this was for some small amount of noise with 4% probability of this and 10. So let's just increase it to 30. So now we are giving 4% probability of impulse noise, but 30 standard deviation Gaussian noise, and just try again. Yeah, so we've got the images. Out here, it's quite evident that the UNF filter is quite better than the median filter. We are getting a 1.6 almost increase in PSNR. And even from the image, it's very evident. This is very, very grainy, and this is quite better. This is quite clearer than this one. Let's now go forward and increase the impulse noise. So we make it almost 10% probability of impulse noise, and then let's just reset the standard deviation and let's see what happens. So we've got our images, and again we are getting a 1.1 decibel increase. Right here, the decibel value doesn't really show much, but it's very evident from the images. So you can see the skin, it's very grainy here, and it's quite clear in the UNF filter. And pretty much that's it. Thank you.